folks, welcome to Whiteboard Science, where we do our best to answer science-related questions as quickly as possible in a reasonable amount of time, keeping them below our goal of about 15 minutes. So I belong to a few groups on social media that are physics, science, astronomy related, and someone posed a question, that is, why, if I have two different things of different mass, when I release them, why will they both hit the ground at the same time? Which is an interesting question, meaning if I have a bowling ball and I have a feather and release them at the same time, why will both hit the ground at the same time? Now, I know what you're thinking. The feather will hit the ground much later than the bowling ball. And that is true, and that's because of air resistance. But we're going to talk about air resistance here in a little bit. If we did not have air resistance affecting the bowling ball and the feather differently, then they would certainly strike the ground at the same time. And that's what we're going to talk about. How does that happen? Why does that happen? And in keeping in accordance with our goal in Whiteboard Science, we're going to try to do this in about 15 minutes or less. So here we go. Let's draw. By the way, that question that was posed, it was posed, and I belong to several science groups, physics groups, whatnot, and social media. And there was a question that was posed. And I said, hey, I can give you a good answer, but I don't want to sit here and type all this out. So let me make a video for you. I think we'll explain it better. And I said to myself, by the way, hey, might as well just put this on Whiteboard Science because it is a pretty interesting question. So we got two objects of different mass. I've drawn them different size here, but we'll assume the larger has the greater mass. And if I release both of these together with an initial velocity of 0, they'll travel some distance from here to here and strike the ground at the same time. And the question is, why does that happen? And we're going to explain that here. The first thing I want to talk about that first, and we touched on it just a little bit, and that was air resistance. So obviously if I have a bowling ball and then some feather like I talked about, and I release them, obviously the bowling ball is going to get there first before the feather because of air resistance. So how do we take care of the question regarding air resistance? Well, the most common thing, and I hear this all the time, and that's what some of the answers that were posted talked about, and that is just say that air resistance is negligible. In other words, just pretend it's not there. Another valid way to have this discussion would be, well, let's just assume we're in a vacuum, meaning, we're here on Earth, but we're going to be in a gigantic vacuum chamber and drop these things in a vacuum where there's no air. Or we could say we're out in space standing on the moon. You can't say we're on Mars because Mars has an atmosphere. Can't say you're on one of the other planets because they have an atmosphere, but the moon does not have an atmosphere. So we could say, well, let's just drop these on the moon and we'll see what happens. And that is valid. And in fact, astronauts did that experiment, and you saw that both, you can look on the video and see that both objects hit the ground at the same time, the lunar surface. But the reason why I'm not a big fan of that is that folks are going to watch this and go to their balconies or go on a ladder or go to a cliff, and they're going to test this. They're going to play around with this. Maybe someone's going to teach one of their friends or their kids or something like that. And yet they can't do this in a vacuum chamber. They're not going to be on the moon. So we have to talk about air resistance. Now, how can we do an experiment such as this and take air resistance out of the equation? Well, I thought about this for quite a while, and it dawned on me, why not just take two plastic spheres like toy balls, wiffle balls would be an example. That's a game, I think it's still around, I don't know, and cut a little slot in it with a razor blade or X-Acto knife and throw some nickels in there. Let's say we put 50 nickels inside this one and 5 nickels inside that one. They both now have the same mass, M1 equals M2, but physically speaking, how the air is going to affect them is identical. They're the same size, the shape. Most likely they came off the same assembly line. They're made out of the same stuff. The thickness of the wall of this sphere is the same as this guy over here. So now we know the total mass of this and this. We haven't affected the mass of these by any stretch of the imagination. They both have the same texture / smoothness. And so when we drop these two things, they ought to drop under the influence of air. However, it's affecting both of these equally. Here's just a very simple example. John and Bob run a race. John wins. He beats Bob to the finish line. And someone says, well, it's because John is younger than Bob. That's why John was able to win. Well, somebody brings to this person's attention, hey, John and Bob are the same age. Well, now we know John did not win due to age if they're both the same age. So we took age out of the discussion, out of the equation, and that's what we do here with air resistance. We take it out of the equation, we take it out of the discussion by dropping two things that are physically identical, same amount of surface area that the air resistance is going to affect, same mass, same texture, same contour. I thought about doing this with those plastic Easter eggs, you know, that you can break in half, you know, pull apart and put some stuff in it and close it back. But then it dawned on me, what when I drop these, if one of these, I'm going to draw two of them here, forget this stuff, what if one of them tumbles a little bit differently than the other one? Well, air resistance is going to affect that one differently. And now we've negated any results from our experiment or our test. So that's the way we're going to get around that. For our video here, I am still going to draw object 1 and object 2 as if they have a different size, but keep in mind they don't. They're inside of those plastic toy balls. But I'm going to draw them differently so we can remember that this one, object 1, we'll call that object 1, object 2. This one has a greater mass than that one. So that's how we'll do that. So let's talk about something real quick. We said that we're going to drop these from some velocity that is 0. In other words, just dropping them together. We know they've got some distance they've got to travel. Therefore, we know if it went from here to here, and in physics we call that displacement. If this thing goes from here to here, then it had to have obtained some velocity. Typically V or A are drawn with little, and F also are drawn with little arrows over them because it indicates that velocity is a vectored quantity. It has magnitude and direction. Well, he went 50 miles an hour. Well, that's great, but in what direction? So velocity has direction and magnitude. So does acceleration, so does force. So oftentimes you'll see these drawn with little arrows over them. But anyway, back to object 1. To go from initial velocity 0 and to have moved from here to here, it had to have obtained some velocity to move. And if it went from 0 velocity to some velocity, whatever that is, it doesn't matter, then we also know that it had to have experienced some acceleration. Pretty straightforward. Had to have experienced some acceleration. Now, this guy named Isaac Newton came up with some physics laws and things like that regarding bodies in motion. One of them said that anything that's at a certain velocity, whether it's 0 or 1,000,000 meters per second, it wants to keep going on that velocity in that direction with that magnitude, unless it's acted upon by some external force. So when I release this, if there wasn't any external force affecting this, it would just stay there. It would not have ever moved. But there's some force affecting it. That's Newton's first law. His second law says whatever that force is, it's equivalent to the object's mass. We'll just put m1 for this object because we're going to talk about this guy, times the acceleration experienced by that object. And that's Newton's second law of motion. And because we're talking about a force not due to some kid pushing on a brick wall or rubber tires pushing against concrete, we're talking about the force of gravity. So oftentimes force of gravity is denoted by F sub g. So F equals ma. And his third law said that, hey, if there's a force in that direction, then whatever that force is applied to always applies an equal and opposite force in the opposite direction. We know that to be true because the tires on our car, when driven by the engine, rotate this way and they apply a force on the ground in that direction. Well, the ground applies a force back in the other direction, which pushes the car forward, and that's how we're able to drive. By the way, incidentally, the car pushing the ground that way actually makes the whole ground move too as well, but because the mass of the earth is so great, the acceleration is so tiny. I'm going to draw a little bitty a. It's so tiny, in fact, that obviously we do not see it. If we had our car mounted on a platform that had wheels under it and we were to press the gas pedal, we would see that platform slide as well as the car go forward. And depending upon which of those two had the greater mass, we would visually see which one was accelerated the most. Sorry about that. So F equals ma. That's the big one we're going to talk about now. F sub g equals m1a. There's our little arrow. We could be technically correct and put one here. So let's talk about this. Another thing that Newton came up with was the formula for gravity the force due to gravity. And the formula specifically is G, that's the gravitational constant, M1, and this is the gravity between two different bodies, mass 1 and mass 2. So F sub G equals G M1 M2 divided by the distance between the two squared. Now this G, gravitational constant, was discovered later in laboratories and through experimentation just to fine-tune this formula a little bit more. Newton did not come up with that. He came up with this. G was added later to the equation, an extremely, extremely small number, 6.67 times 10 to the negative 11th. That is a lot. That means you take 6.67, you move the decimal point over 10 times. That's how small this number is. In fact, it's so small that for the purposes of our discussion, and I'll probably accidentally insert G anyway, we can actually take it out and just say, hey, M1, M2 divided by D squared. So the force due to gravity between two objects is equivalent to the product of the mass of those objects divided by the distance between the two squared. But let's put this back up here that I had earlier. There we go. And suppose we're talking about object 1. Well, we're talking about object 1 and the force of gravity between it and the Earth. So we can replace this 2 with E. So the force due to gravity between object 1 and Earth is equivalent to the mass of object 1 times the mass of Earth divided by the distance between the two. And it's not the distance from here to the surface, it's the distance from here to the center of the Earth. And by the way, if you're trying to lose weight and you want to look thin on a scale, go to the poles and measure yourself, because the Earth is not a perfect sphere. It's a little bulged at the, go to the equator. It's a little bulged at the equator, so guess what? The distance from the center of the Earth is greater at the equator. So if you stand here, you'll find this number is a little bit bigger, which makes this number smaller. So you'd be a little bit lighter on a scale. Not probably enough for any scale that we can buy at a store to detect, but that's an interesting fact. So we have this and we have this. But check this out. If this is equivalent to that, and these two are obviously equal, then let's just move this down to here. M1A, which is the force due to gravity, we agree, equals, now remember we're talking about mass 1, mass Earth divided by D. Now that's ugly, sorry about that. I'm going to get rid of some of the clutter here. Let me rewrite this. So what we had was M1A equals M1 ME divided by D squared. Okay, so what? Well, if we do something to the left half of the equal sign and also do it to the right half of the equal sign, we haven't changed the equation at all. That's basic algebra. So let's multiply both sides by 1 over M1. It's the same as dividing by M1. And what we have is these cancel out and these cancel out. Now again, we haven't done anything to the equation, but what we're left with is acceleration is equal to mass of the Earth divided by D squared. And we haven't done anything magical. It's just some basic algebra. And I'm going to rewrite this over here because it's important that it be available for us to look at. Let me rewrite that D a little nicer for you. So what does this tell us? This tells us that object 1, the gravitational attraction, or the force due to gravity is another term for that, between it and the Earth has no, the mass of the object has no play whatsoever in the formula. Only the mass of the Earth. See that? We don't even have M1 in here anymore because we took it out by dividing both sides of the equation by 1 over M1, multiplying by 1 over M1. So we can have object 2, whose mass is m2, we could have used m2 in these equations and we still would have been left with A equals me, mass of the Earth, divided by d squared. In other words, any object we would want to drop, or any satellite that's in orbit, or any moon that's orbiting Jupiter, Saturn, Uranus, Neptune, or Earth, or Mars. Mars has 2 formal moons. Who cares what their mass is? The force between them and their parent planet is based on the parent planet only. So now we can see why the mass of these two things, when they're different, they still hit the ground at the same time. So let's review real quick. For these two objects to have started with a velocity of 0, v sub 0 means this is initial velocity equals 0. So in other words, no velocity. They moved from here to here, therefore they had to have attained some velocity to do that. And to go from a velocity of 0 to some velocity greater than 0, they had to have experienced some acceleration. How much acceleration? This right here. So they both experienced acceleration. How much? A equals me divided by d squared. Notice that the mass of m1 or m2 is nowhere in this equation, and that is why when you drop two objects of different mass, they both will hit the ground at the same time. Keep in mind, putting these masses inside identical hollow spherical balls, plastic, whatever you want to use, but something so that air resistance affects them both equally. Go do this experiment. You'll find that it works. Here's something interesting that I'll close with, but now you know the basic answer to the question. The actual acceleration due to gravity on the Earth's surface, on average, because like I said, it's different from different places around the Earth, is 9.81 meters per second square, or oftentimes 32 feet. Now, there's a decimal in here. I don't remember what it is because I always use the metric part of it, feet per second squared. That's fast. So that means for every second, it's going to go 9.81 meters. Even more so at second number 2. So the point is, unless you use slow motion photography, you may not, or drop these from a very, very large height, you may not be able to tell yourself, yeah, I can tell that they definitely hit the ground at the same time. In other words, if I drop these from 3 feet, look at this. I mean, how do we know that the dry erase marker actually hit the board first? Because they traveled such a short distance. We know that it will beat this guy to the whiteboard due to air resistance, but unless we drop them from a big height or use slow motion photography, it'd be hard to catch that. So one of the things that you probably heard of his name, Galilei, did, he reckoned, and of course they didn't have cameras and all that stuff back then. He said, yeah, I could drop stuff, 2 different things, and do these falling body experiments, but it's hard to tell because this is happening so fast. So he, being the genius that he is, said, well, let's do this. Here's the ground. Let's put them on a ramp. Because when objects travel down ramps, they're doing so under the influence of gravity. So it's the same force pulling these things down. It's just now they travel in this direction. We're able to slow down the problem. In fact, you could say that this is a ramp that's 100% in the vertical at 90 degrees to the Earth's surface, or we could do a ramp that's 1 degree to the Earth's surface and really slow this down. Or do it at 10 degrees, and I don't know what angle he picked, but he did something so that now he has 2 objects. I'm going to kind of draw this in perspective of different masses, identical ramps, or a single ramp, and we just measure the time and for each of these separately, and he released these, and he was able to see and determine that objects of different mass got to the end of the ramp at the same time. So anyway, that answers our question. Why does objects of different mass strike the ground at the same time when released together? Hope you liked it. If you enjoy Whiteboard Science, subscribe. If you have any questions or comments, please post, and I'll get to them as soon as I can. Thank you very much, and have a good day.